Hi, my name is Mohan Rastanabalan. Today I will present my UGP2 entitled Vortex Induced Vibration Numerical Simulation for Fixed Segmented Cylinder. Before I start my presentation, I would like to inform that due to the pandemic of COVID-19, I have to change my UGP title, which was initially on experimental studies to numerical studies. So there will be some changes done to my objective of the study and to the scope of my study. Presentation outline. For today's presentation, it covers altogether 6 chapters. Chapter 1 Introduction, Chapter 2 Literature Review, Chapter 3 Research Methodology, Chapter 4 Simulation Setup and Validation, Chapter 5 Results and Discussion, and Chapter 6 is on Conclusion and Recommendation. Chapter 1 Introduction. Background of research. Oil and gas exploration continue to advance into deeper and harsher environment. Engineers and designers face more challenging tasks in developing practical riser design for this emerging development. However, the serviceability of the riser, which involved frequently in production, may causing failure on its structure itself. This failure is particularly due to vortex-induced vibration that happens through interaction between riser and the fluid flow. However, with the existence of buoyancy segments on the marine risers may decrease the fatigue damage rate due to decrease in the vortex shedding frequency for its larger diameter to the riser diameter. Buoyancy segment. The following figure shows the schematic of riser with buoyancy element. The resulting VIV of a riser with staggered buoyancy modules depends on the ratio of length of buoyancy segments to the length of gap between two adjacent buoyancy segments. Problem statement. The main point in the problem statement is to investigate under which coverage of buoyancy segment would the VIV excitation on buoyant region dominates the response in order to identify the best design on encountering VIV. Objective of research: to design and develop a numerical simulation setup for segmented cylinder to investigate the VIV response of different length of segmented cylinder to encounter VIV. Scope of research: literature study on previous UGP and related studies, development of simulation setup for segmented cylinder, numerical simulation of even and uneven distributed length of segmented cylinder, and finally analyze the lift and drag response of even and uneven distributed length of segmented cylinder. Chapter 2 is on literature review. VIV of fixed cylinder. The vortex induced vibration are vibration which caused by the vortex shedding from both sides of the cylinder due to fluid motion. The shedding frequency is related to a full periodic cycle for the shedding process. Vortex shedding occurs when an unsteady oscillation flow takes place at certain condition when a fluid flow around the body. Due to the periodic shedding, an asymmetrical flow pattern develops around the body and will change the pressure field distribution behind the body. Important parameters used in the simulation study. The first one is Reynolds number, Strouhal number, reduced velocity, lock-in phenomena, drag and lift forces. Turbulence model. Large eddy simulation. Large eddy simulation is a numerical method which utilized in stimulating the turbulent flow with large scale motion, which must be computed explicitly, and the smallest universal scale are modeled via subgrid scale SGS model. Navier-Stokes equation are partially filtered to obtain governing equation for the LES model. LES require finer mesh than other type of method. Meanwhile, the simulation has to run for a sufficiently long flow time to get a statistics flow. Buoyancy segment. The important things you have to understand when it's come for the buoyancy segment is first the aspect ratio, diameter ratio, and also the spacing ratio. Previous research. The table shows the previous research done by researchers in recent times, especially on best cylinder in either in 2D or 3D. Previous research with staggered buoyancy segments. Research gap. For the research gap, I will use similar length, diameter, domain size, speed range, model dimension, and turbulence model as the research as similar as research done by Adi Maimun et al. And later I present the dimensional data for the present study. Diameter of the cylinder is set to be 114 mm. However, the diameter for the buoyancy segment will be 285 mm. The length of the cylinder will be 3000 mm or 3 meter. For the length of the buoyancy segment, 273 mm. The diameter ratio dB over dr will be 2.5. Spacing ratio of 3/1 and 2/1. Number of modules used for each configuration is 3 and 5, and the coverage percentage is 30% and 50%. The dimension for the buoyancy segment is taken by doing ratio calculation with the real world buoyancy segment to get the dimensional data for the model for the buoyancy segment. Chapter 3, Research Methodology. Research Methodology Flowchart. The research methodology start with literature review on VIV, validation by using ANSYS Fluent with available simulation study on single base cylinder, generate cylinder model with segmented cylinder and meshing, use ANSYS Fluent to study the VIV suppression using segmented cylinder, extract simulation data on lift and drag coefficient, and finally results and discussion. Chapter 4 on simulation setup and validation. ANSYS Fluent have 3 stages. The first one is the preprocessor, the solver and the post-processor. Under preprocessor we have modeling, defining solution domain, mesh generation, fluid properties and boundary condition. Building a model. The model was designed in Design Modeler under ANSYS Student 2020 Workbench. It's a cylindrical model along with the solution domain, and segmented buoyancy modules vary in terms of number of segments. For base cylinder, 30% segmented cylinder, and also for 50% segmented cylinder. Mesh display, simulation setting, fluid properties. When we set the material to be water, by default, the Fluent will give the value for the density and viscosity, and we set the Reynolds number to be in between 30,000 to 90,000. Simulation type is 3D and unsteady, solver double precision, pressure based and implicit, turbulence model, LES model, pressure standard, pressure velocity coupling, simple. For the boundary condition, we set the inlet as velocity inlet, outlet to be pressure outlet, top, bottom and side wall, symmetry, cylinder wall to be no slip wall. Okay, next we see for the solver flow. First we set the viscous model, then we edit the material panel, set velocity condition, set boundary condition, set reference value. It is very important to set a correct reference value, because the value in the reference panel will be used to compute lift and drag coefficient. Set report definition, and finally solution initialization and run calculation. Post processing. At this stage, the visualization image will be presented and some generation of animation contour viewing and particle tracking. The flow pattern created in the solver stage will be reviewed from the animation contour. Grid independency test. The simulation study for base cylinder is carried out as a grid independency test. This was aimed to determine whether the results of the simulation is independent of mesh or not. Validation. The present study reveals similar trend with the published data based on the simulation study done by Wang et al. 2014. Based on the trend shown, the result from the current simulation can be accepted as similar simulation setup is done prior to the simulation, and both studies conducted in 3D computational domain. Chapter 5 is on results and discussion. Base cylinder. The simulation is carried out with base cylinder with several reduced speed ranging in between 4 to 10. The simulation results such as velocity magnetic contour and the vorticity magnetic contour represent as follows for the flow time of 150 seconds for UR equal to 5. Segmented cylinder, 30% segmented cylinder. In order to present the top view of the segmented cylinder, the domain was sliced at 2 different sections. The first section was base cylinder and the second section was the buoyancy segment. 50% segmented cylinder. Okay, next is the analysis of VIV bare and different coverage of segmented cylinder at different reduced speed. Drag coefficient. The following graph shows the graph that extract directly from ANSYS Fluent, and later on we plot the graph in the Microsoft Excel. For base cylinder, 30% segmented cylinder, and for 50% segmented cylinder at the reduced speed of 5. Next is drag coefficient comparison and percentage reduction. The mean drag coefficient for the batch cylinder is 0.829, whereas for the segmented cylinder with 30% and 50% shows 0.625 and 0.462 respectively for reduced speed of 5. The mean drag coefficient is reduced using segmented modules. Comparatively, 50% of segmented cylinder experience more reduction in drag coefficient than 30% segmented cylinder, where each configuration shows 44.27% and 24.61% respectively. A reduced speed of UR equal to 5. Generally, for all reduced speed, it shows the similar trend on the results. Next is the lift coefficient graph extracted from ANSYS Fluent for similar for batch cylinder, segmented cylinder at the reduced speed of 5. Lift coefficient comparison and percentage reduction. The lift coefficient value for the batch cylinder is 0.659, while for the segmented cylinder with 30 and 50% shows 0.209 and 0.179 respectively. For UR equal to 5, the RMS lift coefficient is reduced using segmented modules. Comparatively, 50% segmented cylinder experience more reduction in lift coefficient than 30% segmented cylinder, where each configuration shows 74.6% and 68.29% respectively at reduced speed of 5. Generally, for all reduced speed, it shows the similar trend on the results. Fast Fourier transform analysis (FFT). The FFT analysis aims to calculate the frequency spectrum of vortex shading frequency for bare and segmented cylinder. For cylinder, the vortex shading frequency can be obtained by FFT of lift coefficient. The results are compared and summarized in the following table. Vortex shading frequency for bare and segmented cylinder. The following figure shows the frequency spectrum that extract from Fluent. Next is the frequency ratio comparison. From the ratio comparison, we can see that the natural frequency are far from the vortex shading frequency, and the reduced velocity UR are not in the range of 4 to 10. Hence, for all cylinder model, lock-in is unlikely to happen because the value of the natural frequency is 0.7. But when we see the value of the vortex shading frequency is much lower than the natural frequency. Chapter 6, Conclusion and Recommendation. Conclusion. The result obtained proved that the high coverage of segmented cylinder may act as a suppression model in reducing the vortex-induced vibration near the cylinder surfaces. The graph of lift coefficient value indicates that the fluctuating of cylindrical structure is lower by employing buoyancy segment within the cylinder. Therefore, the buoyancy segment can reduce the vibration of the cylindrical model to increase the fatigue life of the model as well as the marine riser in real-world application. The larger diameter of buoyancy segment breaks the vortices effectively, which occurs behind the marine riser along the certain length. When the sea current flow hits the buoyancy segment, separation happens early on the way. In conclusion, based on the study results, the segmented cylinder with 50% coverage of buoyancy segments selected as the best configuration in encountering VIV. Next is the recommendation. The fluid structure interaction should be near to the real world condition that happens in deep water, see during the oil and gas exploration activities, so that the real situation problem can be solved and can predict the fatigue failure of the structure. An experimental study should be conducted on the present study to precise the results on the present study in terms of verification. In order for lock-in phenomena happens, the value of the natural frequency should be reduced or more wider range of speed should be taken. The following study may include dynamic meshing to study motion of the cylinder due to vibration to propose more accurate results that implies real-world fluid structure interaction. Next, we see for the reference used for the simulation study. And finally, thank you for your time. Thank you.